Now what we would like to do is use the same starting equation, our energy conservation equation, that told us that the kinetic energy at some time plus the potential energy at the same time is equal to a constant total energy, which, as Daniela just explained, is actually equal to 0 in the event that an object is just barely able to escape. And that was the condition we used to find escape velocity. We're going to do the same thing now, but instead of solving for escape velocity, we're going to solve for the radius that you need to be at, away from the center of our black hole, in order to escape, and the radius below which it is impossible to escape. So our kinetic energy, once again, as before, is just the standard 1/2 the mass of our object times its velocity squared. Our potential energy, which we're adding, is going to be a negative number, so adding a negative number, I'm just going to put a subtraction here, and we have g, the mass of our black hole, the mass of the object, divided by the radius of the object, make that darker, and that thing is equal to 0. And we proceed similarly to before. So the first thing I'm going to do is I'm going to add gmm over r to both sides of my equation. So I can do gmm over r plus then 0 plus gmm over r. Okay. And now on the left-hand side here, we see we have a plus gmm over r minus a gmm over r. So these two will cancel out with each other. And then on the right-hand side, it's just 0 plus this value. So that's going to be unchanged. So if I simplify this on the next line, I'm going to get that 1/2 mv squared is equal to g big M little m over r. And one substitution I'd like to make right now is that we're focusing on light. Remember, we're trying to find a condition at which you have a radius below which light cannot escape. And because we're talking about light, light always travels at the speed of light, c. So I'm going to say that my v squared, or just even more simply, my v, whether it's squared or not, is just going to be equal to c. So I'm going to rewrite this exact same equation, changing nothing. Just where I have v squared, I'm going to make now c squared. So I get 1/2 mc squared is equal to g capital M lowercase m divided by r. All right. Now I would like to solve for r. Now, the first step I will take to do this is to just multiply both sides by r, right? So on the left-hand side, we're going to have r times this. And on the right-hand side, we're going to have this times r. So that way on the right-hand side, my r's will cancel with each other. And then I get 1/2 r times m c squared is equal to g big M little m. On both sides we have lowercase m, so I will divide each side by lowercase m. And then they will cancel here and here and here and there. So we get 1/2 rc squared is equal to g capital M. Okay, we're getting close now. We can go a step further and say, since I'm trying to solve for r, we should multiply both sides by 2. So that way this 2 in the numerator and this 2 in the denominator will cancel. And we get that rc squared is equal to g big M times 2. Now I'm going to move just simply move my equation up here so we have more board space. I will rearrange to move the 2 to the left-hand side of this just for aesthetic purposes. I get RC squared is equal to 2gm. Since I'm trying to solve for r, I should now divide both sides by c squared. On the left-hand side, the c squareds will cancel. And we finally find that this r is equal to 2g capital M over c squared. This r is typically referred to as the event horizon of a black hole. And it is the point at which, if you are at a radius smaller than r, even something with the speed of light could not escape your black hole. All right, now we can actually calculate what this is. So, because of our code, we know that r is equal to 2. We said g was equal to 100. And we said that capital M was equal to 1,000. While c is equal to 50. And we square that. And it's easy enough, either through mental math or your calculator, to find that r is equal to 80. So we found that the event horizon is located at 80. And you may recall a moment ago when we were messing around with the code, we ended up changing and getting 80 as the exact value that we expect the event horizon to be. So there's actually no fractional error. There's no error at all. If we found that it was exactly 80 and we measured 80, then in the numerator of our fractional error equation, we're going to have 80 minus 80, which is 0. And then 0 divided by anything is still 0. And therefore, we have no fractional error. So we got pretty lucky in this case. The numbers were friendly, and we chose the right values, and we were head on.